How does quantum theory bridge microscopic and macroscopic worlds? Imagine a tiny particle like an electron behaving both as a wave and a particle at the same time. This strange behavior is part of what quantum theory explains. It helps us understand how the tiny world of atoms and subatomic particles connects to the big world we see every day. Quantum mechanics shows that all matter follows the same rules, no matter how small or large. But as objects get bigger, their quantum effects seem to fade away, and classical physics takes over. This is where the real puzzle begins. How do these tiny particles, with their weird behaviors, build the stable, predictable world we live in? At the microscopic level, particles like electrons and photons can do things that seem impossible in everyday life. They can exist in multiple states at once, a phenomenon called superposition. They can also become entangled, meaning their states are linked no matter how far apart they are. These behaviors have been proven through many experiments and are the foundation of quantum theory. But when we look at larger objects, like a baseball or a planet, they don't seem to do these strange things. Instead, they follow the rules of classical physics, with definite positions and predictable paths. So, how does the world transition from quantum weirdness to classical stability? One key idea is called the Correspondence Principle. It suggests that quantum effects become less noticeable as systems grow larger or have higher quantum numbers. Basically, the more particles involved, the more their individual quantum behaviors average out, making the object appear classical. Another important concept is decoherence. When large systems interact with their environment, their quantum superpositions collapse into definite states. This process makes quantum effects invisible to us because the interference patterns are lost. Plus, measurements on big objects often lack the precision to detect quantum details, so they seem to behave classically. Despite this, some large systems do show quantum behaviors directly. Superconductors are a perfect example. They allow electrical current to flow without resistance because many electrons occupy the same quantum state. Superfluidity is another example, where liquids flow endlessly without viscosity. These phenomena prove that quantum effects can appear at large scales under certain conditions. Recent experiments have even shown that quantum correlations can exist in macroscopic objects, challenging the idea that quantum effects are only for tiny particles. Scientists still face challenges in fully explaining how classical stability emerges from quantum rules. Some believe that our perception of stable, localized objects is influenced by how we observe and measure the world. There might be a need for a more complete theory that goes beyond standard quantum mechanics to fully connect the micro and macro worlds. Understanding this bridge has led to many technological advances. Quantum computers use superposition and entanglement to perform calculations much faster than traditional computers. Superconductors have revolutionized energy transmission, making it more efficient. These innovations come from foundational discoveries in quantum mechanics that continue to shape science and technology today. In the end, quantum theory provides a framework that explains how the strange behaviors at tiny scales give rise to the stable, predictable universe we experience. It shows that the rules governing atoms and particles are the same rules that build the world around us, just in a way that becomes less obvious as systems grow larger.